So good afternoon, Bryn, and anyone else who might be listening. So today we have kind of a little bit longer lesson. Sorry, I think it'll go quickly, but it's kind of a few pages. So what we're going to do today is we're going to identify polynomials and their characteristics. So before we jump into that, I actually made a special graph just for you and your class. So here's an example of a polynomial graph right here. And what it's representing is the temperature of a day starting at, right here, at 6 p.m. And as we know, the temperature drops for a while. And then, so maybe like around midnight or so, maybe it's kind of at its lowest point. And then here we are at 6 a.m. It's kind of on the way up. And then here we are at noon. It's not quite at maximum at noon, a little bit past noon, maybe like 1 o'clock. It gets to maximum, maybe 2 o'clock. Then it comes back down to where it was 24 hours earlier. So this is an example of a polynomial function that represents the temperature of the day. And we could use this, obviously, if we knew some data points. We could say, hey, I was awake here and here, but I wasn't awake here. I wonder what was going on in between. And weather forecasters can use that to find the dew point, whether it's going to be fog, et cetera, et cetera, et cetera. So in any case, there you go. There's an example of a polynomial function that I made up just for you. And there it is right there, plugged in the data. So it's going to be negative 0.0424x cubed plus 1.62x squared minus 13.9x plus 50. So there's an example of a polynomial function. And let's get on with the business of taking a look at the polynomial functions for our class. Okay, so polynomial. So what is a polynomial? Well, it's an expression, often in one variable, usually, involving terms of numbers and or variables, all separated by pluses or minuses, plus or minus signs. So you're already familiar with these things. We've already talked about them. You just don't know that we were necessarily talking about polynomials. So here's a polynomial that we're familiar with. It's just a quadratic. We've looked at lots of these. And here is a linear polynomial. Remember, poly just means many, as in more than one. Here's another polynomial. This one looks a little bit different. And here is a much more extended one, where we have the highest power being 5, 4, 3, 2, 1, 0, all the way down the powers. And that's the way we like to write polynomials, in descending order of power. So these are all examples of polynomials. Again, we've seen them before. You already know what they are. And you can see that each one of these terms is a number and or a variable separated from another number and or variable term by a plus or a minus. That's what these are all about. So pluses or minuses separate them. All right. Polynomials in one variable can't have two variables, or 3 or 4, whatever. They can't have variables in denominators, can't have variables inside square roots or any other kind of roots, and there can't be negative exponents. So explain why each of, so here's some problems that we can do. Explain why each is not a polynomial in one variable. So let's look at the first one. So we got 3x squared plus 4x to the negative 2 plus 9. How come this is not a polynomial? Well, because it's got a negative exponent. So I'm going to write that right over here. Negative exponent. Then we go down to the next one. Let's take a look at this. So we got 7x cubed minus 9 times the square root of x. How come that's not a polynomial? Well, it's got a variable inside a root. Not okay. Let's take a look at this one. We got f of x equals 11 over x plus 7 over x squared. This one's not a polynomial either because it has variables in denom. Not okay. Okay, so like I said, this looked like a whole big sheet right here, but we went through it very quickly. Definition of polynomial, some examples, and some examples of things that ain't polynomials. All right, so let's take a look at the next part. So the two most important characteristics of a polynomial are the leading coefficient and the degree. And so the degree is just the highest power. That's it. It's just the highest power. And the leading coefficient is the number in front of term with highest power. So, naturally, we're going to do some problems where we find the degree and the leading coefficient. So we look right here at this guy right here, g of x. I just decided to change it from f. G of x is 7x to the 8th minus 9x squared plus 3x plus 19. So the degree is the highest power. What's the highest power? 8. So degree equals 8. And the leading coefficient is just the number in front of the term with the highest power. Well, here's the term with the highest power. What's the number in front? 7. So the leading coefficient is 7. And usually the leading coefficient is in the beginning. However, sometimes it ain't. So let's take a look here. We look for the highest power. Here we got 4, 9, 2, and no power here, so we think of that as 0. So the highest power is 9, so the degree equals 9. And then the leading coefficient is, again, the number that's in front of the term with the highest power. So in this case, that's going to be negative 2. So the leading coefficient is negative 2. All right, good. So now let's look at function types. And we're moving right along here quickly because, this is all fairly straightforward stuff. So a constant function we've seen before. I'm just going to draw little tiny graphs of these guys right here. So a constant function, so we got our little xy thing here, just looks like this, straight across. Constant, not changing. That's what constant means, not changing. Not going up, not going down, straight across. Same always. A linear function. We're all familiar with linear functions. I'm going to draw that over here so I get a little extra space. It's just a diagonal line, right? We got a slope and a y-intercept. Y equals mx plus b. This is what a linear function looks like. So y equals mx plus b. We've seen lots of those. And quadratic functions. Well, we know what quadratic functions look like. We've graphed a whole ton of those. They look like parabolas. And so we can have y equals 3x squared plus 2x plus 1. Now, cubic functions, we may be a little less familiar with those, but cubic just means, well, cubes have 3 dimensions, so a cubic function is a function that has a power of 3, such as 4x cubed minus 9x. I just made that up. And what do they look like? Well, they look like this. So they're up here a little bit, and they go across, and they come back down. And a quartic function. Well, you see quart right here. Quart is the root word for 4. So that means the highest power is 4. And I'm just making these up, right? These are just random ones that I'm just making up here. These are not the only quartic functions in the world. And so a quartic function is going to kind of look like a parabola, but it's actually going to look more like a W. But we'll talk about that later. And then quintic, the root word quint, or the prefix quint is for 5. So again, we're just looking at a function whose highest power is 5. I'll just put a negative sign just for kicks. Negative x to the 5th plus 9x to the 4th minus 3. And a quintic function looks like this. So you'll notice here this is straight. This has 1 bend in it. This has 2 bends in it. This has 1, 2, 3 bends in it. So 1, 2, 3, actually 1, 2, something bad happened here. 1, 2, 1, 2, 3, yeah, there we go. So this has no bends, 1 bend, 2 bends, 3 bends. So a quartic, 4, has 3 bends. A cubic, 3, has 2 bends. A quadratic, 2, has 1 bend. So we can see that the number of bends in the graph is 1 less than the power. And so a quintic will have 4 bends in it. So 1, 2, so 1, 2, 3, 4. 1, 2, 3, 4 bends for a quintic, a 5th power thing, 4 bends. So I want to use these last two guys right here. I want you to remember these two pictures here. The first one looks like a W, and the second one looks like a W that went bad. So we're going to take a look at those on the other side. Actually, on the next page. Yep. So let's take a look at those functions again, and we'll draw them in green again. So what we had here was the quartic. Remember, this is the power of 4, x to the 4th. And the quintic, a power of 5. Remember, it looks like a W that's gone bad. So this is x to the 5th. Okay, so here's what I want us to notice. When we have an even powered thing, we're up on the right and up on the left. When we have an odd powered thing, we can see that they go in opposite directions. Up on the right, down on the left. And that's going to be true of every even powered function. Again, if we think about a quadratic function, a parabola, we've graphed tons of those. Right? X squared. Even power, both up. And we could do lots of other examples over here with odd powered things, and one would be up and one would be down. So I've created this clever little table for you. And I'm going to cover up part of the table first and then show you what we got right here. All right, so if we have an even power, such as 2, 4, 6, 8, whatever, then we know that we're going to be up on the right, up on the left, and I gave you a little tiny diagram for what that looks like. A parabola, up on the left, up on the right. And if we have an odd powered thing, then we're going to be up on the right, down on the left. Opposites, right? Up on the right, down on the left. And you'll notice here that the number in front here is a positive 1 and a positive 1. There are no negative signs here. So that's what this is all about, positive. So when we have a positive in the front, a positive leading coefficient, and we're even, it looks like this. Positive odd looks like that. And then we just cover that over and go to this. Oh, that's not going to work very well. So if we are even, and we have a negative in front, like a negative right here, just like when we had a negative parabola, it just goes upside down, so it'll look like this. Right? So even is going to be in the same direction on both ends, but in this case, because it's negative, it's going down. Odd means it goes in opposite directions on each end, but in this case, again, we're just flipping it from what it used to be. It was this way, up on the right, down on the left. Now it's going to be up on the left, down on the right. So it's a handy little table to have. And yeah, and I want to give you one other thing, and then we'll put this and this together, which is actually going to be pretty simple and straightforward. All right, so the solutions to the equation f of x equals 0, and when I say f of x, I mean like x squared plus 9x plus 10 equals 0, or x cubed minus 14x squared plus 7x minus 3 equals 0, or any other polynomial equals 0, because we've been talking about polynomials the whole time. So solutions to the equation f of x equals 0 are where the graph hits the x-axis. That's where the solutions are. It's simple. So let's take a look. So here we have this parabola, which we know is a polynomial. It's a simple polynomial. It's a quadratic polynomial. And we want to know what the solutions are. Well, according to this, the solutions are wherever the graph hits the x-axis. So in this case, the graph hits the x-axis right here at positive 1, right here at positive 3. So the solutions are x equals 1 and 3. And we put a little box around that. We don't put parentheses because then it becomes an ordered pair, like an xy thing. So what are the solutions? Where does it hit the x-axis? That's all we need to know. And if we just want to know how many, all we need to do is count how many times does it hit the x-axis. 1, 2, 2 times. Okay, so we're going to combine this and this concept to answer the next questions. So I'm actually going to open up the page so we can use our little table here. Okay, so here we have, all right, so actually one more of these. So back to the concept that we have right here, which is the solutions to the equation are where the graph hits the x-axis. So let's take a look at that. So here's what I want to know. how many solutions does this guy have here? How many real solutions? It's really simple. Just count. Where does it hit the x-axis? 1, 2, 3. The answer is 3 real solutions. Because hits the graph there, or hits the x-axis there once, twice, 3 times. 3 real solutions. And if we had to kind of guess what they were, we could say something like -1, +1 1/4, positive, I don't know, 4. Something like that. I just made those numbers up. Okay, now we're going to combine these two things. How many solutions, and whether it's even, odd, etc. So now we're going to need that table again. Okay, so here's what I want you to find out. I want you to find out about the end behavior. I want you to tell me what that is. So it's either up on the right, down on the left, or, whatever, that sort of thing. Then I want you to tell me whether it's even or odd, whether it's positive or negative, leading coefficient, and how many real zeros. So actually, let's start off with the how many zeros thing, because that's really easy. We just need to count where it hits the x-axis. So here we are. So we're going to do part D first. So let's put D over here. So how many places that hit the x-axis? 1, 2, 3, 4. The answer to D is 4. There are 4 real zeros. Okay, let's talk about the end behavior. So the end behavior is what's going on at the ends, the right end and the left end. So here we are at the right end, and clearly it's going up. So we're going up, right. And what's happening on the left? Going up there too. Up, left. So we did that. And then B, is it even or odd? Well, that's easy. From the table, we remember that even means we're going to go in the same direction on the ends, either both up or both down. Let's take a look over here. Well, these are both up. So it must be that we are of even degree. Run out of room for C there. I'll just put C right here. So does this have a positive or negative leading coefficient? Well, we see that this guy is up. These are both up. So we know that we're even. And is this going to be positive or negative? I don't know. Go back to the table. Well, I see up here and up here, which is what I got over in the problem. And so it's up on the right, up on the left. So it must be even and positive. So even and positive. That's what we're looking for. We're looking for the positive part. All right. So let's do the same trick down here. So here we have a different function. And of course, we know this is a quadratic. And so this should be pretty easy for you. So first of all, we're going to answer part D. How many real solutions? How many real solutions? Easy. It is 2. 2 real solutions. 1, 2. Let's go to A. Let's talk about the end behavior. Well, down on the left, down on the right. So A is down on the left, down on the right. Part B. Is this guy going to be even or odd? Well, they're both in the same direction. Must be even. Part C. And down means odd. Down means negative. It's right in the table, by the way. All right, both down, even, negative. Both down, even, negative. Okay, we got one more of those to do. Keep the table handy, and we're almost done. We're going pretty well here. We'll keep it under 20. All right, so here it is. We got A, B, C, D again to do. So what I want to know is how many real solutions are there? Simple. 1, 2, 3. 3 real solutions. And then we're going to talk about the end behavior for part A. Well, we're down on the right, up on the left. Down on the right, up on the left. Part B was, is this even or odd? Well, they're going in opposite directions, so must be odd. And part C, is this going to be positive or negative? Well, we have to go back to our table for that. And so we're looking for up on the left, down on the right. Let's see if we can find up on the left, down on the right. Up on the left, down on the right means we have odd, negative. Odd power, negative leading coefficient. So we already had odd power. We just need now to fill in negative leading coefficient. Okay, last bit. Simplest thing that we have to do here today. So, and you've already done it. So find a given function value. So here's your function, f of x equals 4x cubed minus 2x plus 1. I want you to find f of 2. What does that mean? Well, it just means put the 2 in there and put the 2 in there, right where the x's are. So we're going to have 4 times 2 cubed minus 2 times 2 plus 1. And so, of course, order of operations tells us we got to do the exponent first. So 2 to the third power is 8. So now we got 4 times 8 minus 2 times 2 plus 1. Now we do all our multiplies. 4 times 8 is 32. 2 times 2 is 4. And then we add and subtract left to right. 32 minus 4 is 28, plus 1 is 29. And there's the whole lesson, Bryn, and hopefully somebody else is listening. So in any case, hopefully that went well, and it's 21 minutes. Sorry, it's a little longer than I wanted. But hopefully you guys are safe and enjoy your weekend, and I will see you on Tuesday. Bye.